Good day everyone. My name is Veshan Anatlaki Rajan and today I'll be presenting the introduction and background of our project. So let us dive into the introduction first. Structural failures in reinforced concrete buildings can pose serious safety risks, increase repair costs and reduce the overall performance of a structure. Therefore, investigating the causes of structural distress is important to ensure that buildings remain safe, durable and serviceable throughout their design life. In modern construction, post-tension concrete systems are widely used because they allow longer spans, reduce the depth of structural members and create larger open spaces. However, if the design, construction process or post-tensioning procedure is not carried out properly, structural problems such as cracking may occur. So now let us go through to the background of our project. So for this project, we investigated a 5-story reinforced concrete parking garage that experienced significant cracking shortly after construction. The building was constructed using long-span post-tension beams and hollow core slabs. It was designed as an unbraced reinforced concrete frame to provide a large column-free parking area. To speed up the construction process, the post-tensioning force was applied only 3 days after the concrete was cast. However, within 5 to 6 days after stressing, cracks wider than 0.7 millimeters appeared in both the beams and columns. This indicated that the problems affected the entire structural system rather than just one isolated area. Our investigation focuses on identifying the possible causes of these cracks by studying the structural loading, post-tensioning effects, construction sequence, and the time-dependent behavior of concrete, including creep and shrinkage. Based on our finding, we also propose suitable recommendations to help prevent similar structural failures in future projects. Thank you.
Okay, so next we proceed with material and structural. So concrete material assessment. First one is a concrete material assessment is to verify whether the concrete had achieved sufficient strength before post-tensioning was applied. The second one to extract concrete core samples to determine the actual compressive strength and compare it with the design value. So the third one is to measure the modulus of elasticity, shrinkage and creep to evaluate the stiffness, deformation and long-term behavior. So next we go with the reinforcement and post-tensioning assessment. Post-tensioning assessment is to inspect zones for cracking, grout leakage and bearing plate deformation. So other than that is also to use we need to use the ground penetrating radar GPR or reinforcement scanners to locate reinforcement and tendon profiles. Other than that is also to identify any construction defects or deviations that may have contributed the observed cracking. So the last one is to check concrete cover, reinforcement spacing and tendon alignment against the drawing. So the last one for the structural and material assessment is to structural evaluation and non-destructive testing. So the first one is to conduct ultrasonic pulse velocity. It's the testing to detect the internal cracks, voids, honeycombings and concrete defects. So other than that, it's also carry out a detailed crack mapping by recording the width, the length, orientation and distribution of cracks. The third one is to monitor crack development over time to determine whether the cracks are stable or still propagating. So the last one for the structural evaluation and non-destructive testing is to integrate all inspection and testing results into the structural analysis to determine the root cause of the structural distress.
Hi, my name is Muhammad Hadif bin Abdul Malik and I will explain about structural analysis. For case 1, which is gravity load only. We get design load is 126.47 kN per meter. After that, we calculate the shear force. For the left side, we get 986.5 kN and for the right side, we get negative 986.5 kN. And for the column, both of them we get is 1125.8 kN, which is constant rectangular block. And then we use moment distribution table to get moment for each member. For the left side and right side, we get 2044 and 9 kilonewton meter, and for the middle moment, we get 1802.4 kilonewton meter, and for the column at the base, which is joint A and D, we get 1021.9 kilonewton meter, and also at the top, which is joint B and C, we get 2044.9 kilonewton meter.
And now for the next part. My name is Reza Izul Hadari Berizalman. I will explain case 2, which is the analysis of the frame under gravity load together with post-tensioning force. So from the case 1, the gravity load was calculated as 126.47 kN per meter. And then for case 2, we include the effect of post-tensioning force by using the equivalent load method. The assumed effective post-tensioning force is 2,500 kN with the tendon eccentricity of 0.2 meter. And using the related formula, the equivalent outward load from post-tensioning is 16.44 kN per meter. This outward load reduces the gravity load, so the net load acting downward on the beam become 110.03 kN per meter. And after that, we use the moment distribution method. The distribution factor are the same as case 1 because the frame size and stiffness do not change. And from the calculation, the final beam support moments are about negative 1779.1 kN meter at both joint B and joint C, while the mid-span moment is positive 1568.1 kN meter. And then for the shear force diagram, the beam shear start at positive 858.3 kN at joint B and decrease linearly to negative 858.3 kN at joint C. The column shear is constant about 988.2 kN. And then lastly, post-tensioning also introduced axial compression in the beam. The beam carries around 2,500 kN compression due to the post-tensioning force. And this is important because although post-tensioning reduces the bending and shear, it also creates a compression and possible restraint effect at the beam column joint. So the case 2 show that post-tensioning reduces the gravity effects, but it must be controlled properly because it can still contribute to cracking if applied too early or if restraint is not considered.
Assalamualaikum, and for this session, I will present the comparative assessment between case 1, which is subjected to gravity load only, and case 2, which is subjected to gravity load together with post-tensioning. Based on the analysis, case 1 shows better overall structural performance under gravity load. Under gravity loading, the slab experienced normal bending behavior with no significant defects. The stress remained within the design limit, allowing the slab to perform as expected. On the other hand, case 2 developed significant cracking after post-tensioning. The main reason is that the tendons were stressed only 3 days after concrete casting. At this stage, the concrete had not yet reached sufficient strength to resist the high pre-stressing force. As a result, tensile stress exceed the concrete capacity and cause crack, particularly around the anchorage zone. And in addition, creep and shrinkage further reduce the effectiveness of the pre-stressing force, increasing deformation and contributing to the crack development over the time. And to prevent this problem, several improvements are recommended. And first, post-tensioning should only be carried out after the concrete reach the required design strength. And second, proper curing should be maintained to minimize shrinkage and improve concrete quality. Lastly, continuous quality control should be implemented to ensure the concrete strength is verified before stressing begins. And in conclusion, although post-tensioning can significantly improve structural performance, it must be applied it must be applied at the correct time and under proper construction control. Otherwise, it may lead to premature cracking and reduce the durability and serviceability of the slab.